This is Hariverse. 3i Atlas is changing again, and the latest observations are difficult to explain. If this video helps you see the mystery more clearly, please like, subscribe, and share. Thanks for watching, and thanks for supporting Hariverse. 3i Atlas remains under steady observation as it recedes from the Sun, and the expectation seems straightforward. An object that behaves like a comet should quiet with distance. Sunlight warms an active surface less and less. Gases escape more slowly, and the visible cloud around the nucleus should thin. A simple chain follows from familiar physics. Less heat means less sublimation, the process where ice turns directly into gas. And less gas means less dust lifted from the surface. As the object travels outward, that chain should tighten into a slow fade, with fewer surprises and fewer sharp features. What draws attention in the recent reports is not only that 3i Atlas stays active, but that certain structures seem to strengthen as the Sun's influence should weaken. Observers describe a sunward-pointing extension that stands out more clearly than before. In the standard picture, sunlight and the solar wind act like a steady push. Solar radiation pressure is the persistent shove of light on dust grains. The solar wind is a stream of charged particles that drags ionized gas outward. Together, they tend to sculpt a comet into a bright head and a tail that points away from the Sun, sometimes split into a dust tail and an ion tail, each shaped by different forces. In that ordinary story, any sunward feature should be the weaker, more delicate thing, and it should become less obvious with distance. A sunward feature is not automatically impossible. Astronomy already has the idea of an anti-tail, and it is often explained as perspective rather than defiance. Dust released earlier can spread into a thin sheet along the comet's orbit. When Earth views that sheet nearly edge-on, the dust can project as a narrow spike that appears to point toward the Sun. In that case, the dust is not truly moving sunward. Geometry turns a broad distribution into a bright line, and the eye reads it as a jet-like extension, even though it is mainly a viewing effect. A natural anti-tail of that kind can appear strong for a while and then fade as the viewing angle changes, leaving the usual away from the Sun tails as the dominant features again. The emphasis in the sample account is different. The sunward extension does not present as a brief alignment that comes and goes. It is described as persistent and increasingly prominent at a time when it should be shrinking into the background. The coma itself, the roughly rounded cloud around the nucleus, is also described as leaning toward the Sun. Even in images without specialized filtering, the brightness distribution appears to favor the sunward side rather than being swept cleanly away. The result is an impression that is difficult to dismiss with a single familiar explanation. Material seems to be presented toward the Sun while the object is on its way out, as though the usual outward sculpting is not in full control of the scene. Distance matters because, for most comets, the Sun is the engine of the display. Close to the Sun, heat penetrates surface layers, trapped ice escapes, and gas flow can carry dust with it. Jets form when gas escapes through cracks or porous channels. Those jets can be narrow near the nucleus, but they tend to widen with time as particles drift outward and sunlight pushes on them. Farther from the Sun, energy input drops rapidly. Activity can persist if the object contains ices that vaporize at lower temperatures, but the general trend still points toward less drama, not more. In that setting, a growing sunward structure is not just another jet. It becomes a statement that something about the material, the geometry, or the source of the activity does not fit neatly into the simplest comet model. Direction is where the ordinary picture strains most. Near the nucleus, a natural jet can point in many directions, depending on where vents open and how the nucleus rotates. Over larger distances, external forces shape what is visible. Dust tails curve because dust particles respond gradually to sunlight while continuing along the object's path. Ion tails can be straighter because the solar wind captures charged gas quickly. Under those influences, the most extended features tend to align away from the Sun, and their overall sweep becomes easier to predict as distance increases. The sample account describes the opposite kind of clarity, a sunward feature that becomes easier to see, alongside additional jets that do not simply fall into a single away from the Sun direction. One conservative family of explanations focuses on particle size. Larger grains are harder for light to push. If 3i Atlas ejects unusually large particles, those particles could maintain their launch direction longer before radiation pressure reshapes their paths. That would help a narrow feature remain narrow closer to the nucleus, and it could delay the formation of a more familiar tail. Yet, large particles are also harder to loft. They require stronger gas flow, which is usually easier to produce nearer the Sun, not farther away. That trade-off does not eliminate the idea, but it turns it into a balancing act. The particles must be large enough to resist being swept back immediately, but the object must still be able to release them efficiently while sunlight is weakening. Collimation adds another constraint. A tightly confined jet suggests a stable source region and a stable orientation, or repeated ejections aligned in a consistent way. Natural comets can show persistent jets if an active area sits near a rotational pole, so rotation does not sweep the jet into a broad fan. Natural comets can also show multiple jets if several vents activate. The sample account, however, stresses that the sunward component becomes the dominant feature, while other jets appear at angles that are not simply away from the sun. The picture that forms is not of a nucleus spraying material in all directions and letting the solar wind sort it out. It is of a structure that keeps its identity, keeps its narrowness, and keeps its sunward orientation when the environment should be eroding those traits. Technique becomes part of the mystery because faint objects are interpreted through careful processing. Smooth coma light can overwhelm subtle structure, so analysts often suppress the circular glow to reveal linear features. That approach can expose real jets, but it can also exaggerate any linear asymmetry already present in the data. The sample account treats this as an important test rather than a shortcut. The behavior of 3I Atlas is compared against other comets treated with the same methods, and the difference is presented as stark. If ordinary comets show jets that largely align with the outward flow, while 3I Atlas shows a strong sunward component under the same treatment, then the anomaly is not merely a trick of software. It becomes a question about what the object is releasing and how that release interacts with the forces around it. By early January of 2026, the narrative settles into a stubborn contradiction rather than a single sensational claim. 3I Atlas moves outward, and the sun should gradually lose its grip on visible activity. Yet, observers describe an anti-tail-like structure that becomes more obvious alongside jets whose orientations do not settle into a familiar pattern. This does not establish an extraordinary explanation on its own. It establishes a problem statement that refuses to go away. An object that should be fading appears to be sharpening its sunward face when the rules suggest it should be turning quiet and trailing away. A tail is a simple label for a measurable struggle between sunlight, flowing gas, drifting dust, and the stream of charged particles that leaves the sun. When a small icy body enters the warmer parts of the solar system, heat reaches the surface and the near-surface layers, and some ices change directly from solid to gas, a change called sublimation. Escaping gas expands outward and can carry dust with it, building a coma that later feeds the tails. A conventional comet commonly shows two main tail components. One is a dust tail, made of solid grains that range from fine powder to larger particles. Dust departs with the comet's orbital motion, so it initially travels alongside the nucleus, but sunlight exerts radiation pressure, a small and persistent force that pushes dust away from the sun. Smaller grains respond more strongly than larger grains, so the dust tail often curves and broadens into a smooth sweep that changes gradually with time and viewing angle. The other main component is an ion tail, made of gas that becomes electrically charged or ionized when sunlight breaks molecules apart and strips electrons away. Once ionized, that gas is caught by magnetic fields carried in the solar wind, and it is drawn outward. This ion tail tends to be straighter and more strictly oriented away from the sun than the dust tail, and they can change quickly when the solar wind changes. Direction becomes a basic test because these forces have a preferred orientation. Close to the nucleus, a comet can look complicated. Jets can erupt from vents and point in many directions at the instant of release, depending on where an active patch sits and how the nucleus rotates. The sunward side can even look brighter very close in because that is where fresh material is being produced. But after release, dust grains and gas clouds respond to the environment. Dust is steadily pushed away by sunlight. Charged gas is swept away by the solar wind. Over large distances, the extended structures are expected to point away from the sun, even if the inner coma shows local asymmetries. The phrase antitail is used when a bright extension appears to point toward the sun, and it matters because it sits on the boundary between ordinary geometry and unusual physics. In the most widely known natural explanation, an antitail is not a stream of material flowing sunward at all. It is a trick of viewing angle. Dust released earlier does not disappear quickly. It can spread into a thin sheet close to the plane of the comet's orbit, sometimes described as a dust trail. If Earth views that sheet nearly edge-on, the sheet can project as a narrow line that seems to point sunward, even though the dust is mainly arranged along the orbit. Such a feature can be striking, yet it does not require any material to fight the outward push of light in solar wind. It also tends to be temporary, changing as geometry changes. The sample account emphasizes another picture and treats it as a physical test. It suggests that a sunward feature could arise if comparatively large particles are launched in a narrow stream, and if their initial momentum carries them toward the sun for a limited distance before sunlight and the solar wind reshape their motion. In that picture, outgassing behaves like a short-lived exhaust, accelerating grains out of a vent. If those grains are larger than typical tail dust, they are pushed less by light, so they can hold a tight shape for longer. The sample frames a scale of roughly 500,000 kilometers as a plausible distance over which such a sunward extension might remain coherent before external forces finally dominate. It is an argument built from familiar ingredients, yet it carries a built-in expectation. The farther the object gets from the sun, the weaker the outgassing should become, and the less capable it should be of launching a prominent sunward stream in the first place. Both natural explanations therefore set predictions that are easy to compare against later images. A projection-driven antitail should wax and wane with viewing geometry, rather than steadily intensify while the object recedes. A momentum-driven sunward stream should weaken as the energy source fades, and it should be accompanied by an increasingly prominent conventional tail once sunlight and solar wind regain full control of the released material. This is why the sample treats the recent behavior of 3I Atlas as more than a curiosity. The claim is not simply that a sunward feature exists, but that it becomes more obvious at a stage when the basic comet engine should be slowing down. The sample adds a second detail that deepens the tension. Even without specialized filtering, the coma brightness appears to lean sunward, as though the inner cloud itself is organized in the wrong direction. If that description matches the underlying data, then it is not only a thin spike that needs explanation, but the general distribution of material close to the nucleus. Comparison is used as a guardrail against overinterpretation. Many comets processed to suppress the smooth, circular coma glow reveal jets, and those jets can look dramatic. Yet, in conventional comets, the extended patterns still tend to organize into an outward flow shaped by light and solar wind, even when several jets emerge from the nucleus at once. The sample points to this contrast as a way to keep the discussion grounded. If the same methods reveal orderly outward jets in ordinary comets, but reveal a dominant sunward structure in 3I Atlas, then the difference is more likely to be in the object, not in the technique. Within a cautious scientific frame, ordinary causes are still tested first. Particle size and density can change how sunlight acts, and a population of unusually large or compact grains would be pushed less and could remain narrow for longer. Composition can matter too, because different ices can remain active at different temperatures, allowing outgassing farther from the sun than a simple water ice picture would suggest. Orientation can matter, because a nucleus with an active region near a rotational pole can keep a jet pointed in a stable direction for long intervals. Yet the sample insists that, taken together, the direction, persistence, and apparent strengthening of the sunward feature remain difficult to reconcile with the simplest expectations. By clarifying what a tail should mean, the mystery of 3I Atlas becomes more precise. A tail is a record of forces, and those forces are not obscure. When the record looks inverted, the question is no longer whether an image is striking, but what combination of material, outflow, and geometry could keep a sunward structure visible while the object retreats into colder space. The most unsettling claims about 3I Atlas do not begin with a dramatic photograph, but with a quieter question about how a faint object is made visible at all. A comet far from the sun is a difficult target. Its coma can be dim, its fine structure can be buried in a smooth glow, and even a powerful telescope can record an image where the brightest component overwhelms the subtle shapes that carry the real clues. Astronomers therefore rely on careful processing, not as decoration, but as a way of separating structures that are physically different, even when they overlap in the same field of view. The sample account places unusual weight on one particular approach because it is designed to remove what is simplest in a comet image, the near-circular brightness around the nucleus, and to leave behind what is least expected, the narrow, non-circular features that suggest directed outflow. The method is often described in plain terms as a rotational subtraction filter, and the basic idea can be understood without mathematics. A comet's coma, when seen at modest resolution, is frequently close to circular around the nucleus, like a bright fog that fades with distance. If that circular glow is duplicated and rotated around the nucleus, the rotated copy still looks almost the same because circles remain circles under rotation. When the rotated copy is subtracted from the original, the circular part cancels out. What survives are the parts that do not match under rotation, the straight or curved features that shift position when the image is turned. Jets, arcs, and asymmetries become clearer because they do not cancel in the subtraction. The sample uses the name Larsen-Sekanina for this approach, reflecting a long history of comet analysis where this technique is used to expose jets that are otherwise lost in the coma's smooth light. The crucial point is that this is not an exotic trick reserved for one controversial object. It is applied to many comets. That makes it valuable as a comparison tool. If two comets are processed in the same way, and one reveals a set of jets that fit familiar patterns, while the other reveals a geometry that strains those patterns, the difference is harder to dismiss as merely an artifact of processing. Yet processing does not grant certainty by itself, and the sample implicitly recognizes this by emphasizing method and context. A rotational subtraction filter depends on choosing a center point, usually the nucleus or the brightest part of the coma. If the chosen center is slightly wrong, subtraction can create false edges. If the comet moves between exposures, stacking must account for that motion, or the nucleus will blur and the filter will amplify the blur into features that look like jets. If the field contains stars, their streaks or residual traces can also leave patterns after subtraction. These are known risks, and for that reason, the most convincing results come from careful alignment on the comet, often with additional steps to reduce background stars and to account for any radial shift of the coma. The sample mentions that a shift can be added if the comet moves in the image, a reminder that the technique is used with the object's motion in mind, not applied blindly. In ordinary cases, when the filter is applied correctly, the revealed jets behave like a second language that still follows the grammar of the first. A natural comet can show two jets, or several, depending on how many active areas open on the nucleus. Those jets can appear to rotate in successive images as the nucleus spins, producing a spiral pattern in the inner coma. They can brighten and dim as active regions enter and leave sunlight. But over time, the overall direction of the extended structures tends to settle into a familiar relationship with the sun. The solar wind and solar radiation pressure do not force every jet to point the same way at launch, but they do shape what remains visible at larger distances from the nucleus. In many processed images of typical comets, the jets seem broadly organized into a general away from the sun orientation, or at least into a pattern that can be explained as a rotating nucleus feeding material that is then sculpted outward. The sample uses that ordinary behavior as a baseline because it places 3i Atlas against it and finds a mismatch that appears not subtle but structural. When the same filtering is applied to 3i Atlas, the sample describes a sunward component that becomes one of the most obvious features rather than a marginal one, along with additional jets that do not simply align away from the sun. Some appear to follow the solar wind direction, while others seem closer to perpendicular, producing an image that reads less like a familiar comet and more like an object with multiple directed emissions that refuse to be sorted into the usual outward flow. The effect is amplified by the central claim that even without filtering, the coma brightness appears to lean sunward. If that is accurate, then the filter is not creating a sunward structure from nothing, but sharpening an asymmetry already present in the raw light distribution. The filter then acts like a contrast lever, pulling hidden structure out of the glare so that the geometry can be evaluated. This is where the sample's approach becomes methodical, rather than merely provocative. It treats image processing as a test, not as proof. The question is not whether a filtered image looks strange, but whether the same filter produces ordinary results on ordinary comets and extraordinary results on this one. In that framing, comparison is the stabilizing force. If a comet discovered in the past few years, processed with the same rotational subtraction method, reveals jets that appear consistent with a rotating nucleus and outward sculpting, then the technique is behaving as expected. If 3i Atlas, processed in the same way, repeatedly reveals a narrow sunward feature that appears tightly confined and persistent, then the anomaly belongs either to the object or to a systematic issue in how this particular object is being processed. The latter possibility cannot be ignored, but it is testable. It demands consistency across independent images and independent processing, and it demands that the feature appears in data that are not all produced by the same person or the same pipeline. The sample leans toward the idea that this test is being met, because the described features persist across time, including a July observation and a January observation separated by months. In the careful documentary tone that follows, the mystery begins to shift from a question of appearance to a question of mechanism. The filter can reveal jets, but it cannot manufacture the physical conditions that keep a jet narrow, keep it bright, and keep it oriented in a way that seems disfavored by the sun's outward forces. The processing step therefore becomes a gateway. It removes the comforting blur of the coma and leaves behind the sharp geometry that invites explanation. If 3i Atlas were expected to become quieter and more conventional as it recedes, then a filter that reveals increasing structure does not merely show more detail. It shows that the object is still producing organized outflow, and it shows that the organization itself is what looks unusual. Hubble enters the story because it removes many of the ordinary reasons a faint image can be doubted. From the ground, the atmosphere is always interfering. Turbulence softens edges, thin haze alters contrast, and a dim comet can look different from one exposure to the next, even when nothing physical has changed. With 3i Atlas, the argument turns on narrow structures and subtle asymmetry, so stability matters as much as power. A telescope that observes from above the air is not automatically right about what it sees, but it does narrow the list of excuses. The Hubble Space Telescope is launched on April 24, 1990, and its early days deliver an uncomfortable lesson about trust. Soon after deployment, the first images show a blur. A tiny error in the shape of the main mirror, a spherical aberration, spreads light into a halo and steals sharpness from the very instrument meant to set a new standard. The solution arrives later through a servicing mission that adds corrective optics and upgrades, a practical set of changes that restores the telescope's intended performance. That history matters here because it keeps a quiet question alive behind every later claim. Is the instrument faithful to the sky? After correction, Hubble's behavior is measured and predictable, and its observing conditions are consistent in a way ground-based observing rarely is. When a faint structure appears repeatedly in Hubble observations, the space for mundane misinterpretation shrinks. This does not guarantee that any interpretation is correct, but it strengthens the case that something real is being recorded rather than a transient effect of weather, variable seeing, or a camera behaving differently from one night to the next. Comets are well suited to this kind of scrutiny. Their nuclei are tiny and often buried inside their comae, and their most informative features can be thin jets that vanish into a smooth glow. Even when a comet is bright, the inner coma can be so round and so dominant that it hides directional structure, leaving only a general impression of a head and a tail. This is why a standard processing method becomes central in the sample account. A rotational subtraction approach, often linked to the Larsen-Sekanina technique, aims to remove the circular coma light so that non-circular features stand out. The idea remains simple even when the results look complex. A smooth circular glow looks nearly the same after rotation around the nucleus, so it cancels when a rotated copy is subtracted from the original. Jets and other asymmetric structures do not cancel because rotation shifts them to new positions and subtraction leaves their mismatch behind. In comet work, that mismatch can be the difference between a feature that is merely suspected and a feature that can be traced, measured, and compared across time. The reason this matters for 3i Atlas is that the method is not reserved for unusual objects. It is a routine tool for analyzing ordinary comets, and that makes it valuable as a comparison test. When the same processing is applied to a conventional comet, jets can look dramatic, yet they still fit within a familiar framework. Material leaves the nucleus from vents, the nucleus rotates, and sunlight and the solar wind shape what is seen on larger scales. The extended structures tend to organize into an away-from-the-sun pattern, even if individual jets point in different directions close to the nucleus at the moment of release. In other words, a conventional comet can be messy up close and still behave predictably when the environment takes over. The sample claims that 3i Atlas behaves differently under that same controlled separation. An earlier Hubble image from July 21, 2025 is treated as a baseline, and a later image from January 7, 2026 is presented as a sharper statement. In that later observation, rotational subtraction is described as revealing a triple jet structure. One jet dominates and points sunward, described as an anti-tail jet rather than a conventional tail. The feature is portrayed as tightly collimated, meaning it stays narrow rather than spreading quickly into a fan. And it is described in proportions as about 11.6 times as long as it is wide. The sample places weight on that proportion because it suggests sustained organization, not a brief smear of dust. It also claims that the two lesser jets are arranged with a striking regularity in angle, and that their orientation is not simply the expected sweep away from the sun. The claim is not left entirely to processed imagery. The sample asserts that even without special filtering, the coma brightness appears to lean toward the sun, so the filter is emphasizing an asymmetry that already exists rather than manufacturing a dramatic line from noise. If that is accurate, then Hubble shows the same oddity in two forms: a raw light distribution that looks organized the wrong way, and a processed view that isolates the narrowest structures. The method becomes less like enhancement and more like separation, peeling away the smooth glow that can hide small but important geometry. A cautious reading still keeps perspective on the table. Antitails can appear naturally when dust spreads along an orbit and is seen nearly edge-on, producing a projected spike that seems to point sunward even though the dust is not truly traveling toward the sun. That effect is known, and it can be strong under the right geometry. Yet, the sample argues that the behavior of 3I Atlas is difficult to reduce to geometry alone, because the sunward feature is portrayed as unusually prominent relative to any conventional tail structure, and because it becomes more obvious at a stage when the object is farther from the sun and expected to quiet. The sample also gestures toward how anomalies are handled in practice. A discussion that makes the anti-tail central can be treated as niche, not because anyone is hiding data, but because science tends to wait for repetition, independent processing, and a path toward an ordinary explanation. That caution is sensible, and it is one reason comet science has avoided many false alarms. But caution has a side effect. It can slow the moment when an outlier is treated as a genuine challenge rather than an awkward exception. Hubble's role, therefore, becomes a constraint rather than a conclusion. Its corrected optics and repeatable imaging narrow the space for instrumental error. Its use of standard comet processing methods strengthens comparisons with ordinary comets. It does not say what 3I Atlas is, but it sharpens what must be explained: a persistent, tightly confined, sunward-oriented structure that remains prominent as the object travels outward, at the very stage when a natural comet is expected to grow quieter rather than more organized. The image dated January 7, 2026 becomes a pivot, because it does not merely repeat what earlier observations suggest. It sharpens it into a geometry that seems harder to soften with ordinary explanations. In the sample account, this observation is described as a Hubble view processed with the same rotational subtraction approach used on other comets, a method that suppresses the near-circular coma glow and emphasizes narrow, non-circular structure. What emerges is not a faint hint, but a clear triple pattern: one dominant jet and two lesser jets, all originating close to the nucleus region and extending outward as distinct features. The dominant jet is identified as the anti-tail, the feature that appears to spear toward the sun rather than away from it. Its description is not casual. It is called tightly collimated, meaning it holds a narrow width over a long distance instead of fanning out quickly into a diffuse plume. It is also described in a proportion that is meant to be diagnostic rather than decorative, extending about 11.6 times as long as it is wide. In ordinary comet imagery, jets can begin narrow, yet over distance, they typically widen and blend because dust disperses and external forces reshape the stream. A structure that remains narrow and coherent at scale hints at either unusual material, unusual release conditions, or an orientation that stays stable relative to the environment. The two lesser jets in the same processed view add to the sense that this is not a single odd streak. The sample describes them as separated by similar angles, an arrangement that looks orderly rather than random. Their orientations are also presented as strange in a specific way. Instead of both falling neatly into the outward direction expected from familiar tail behavior, they appear closer to perpendicular to the solar wind direction inferred from the scene. A conventional comet can show multiple jets at the nucleus, but the extended structures usually surrender to the dominant outward sculpting. Here, at least in the interpretation presented, the outward sculpting does not dominate the visual story. The anti-tail is not a minor sunward accent. It is described as the major feature, and that prioritization is one of the central tensions. If the sun is the engine and the solar wind is the sculptor, then the strongest, longest feature should usually align with the outward flow, not against it. The sample leans on this expectation and then points to what appears to violate it. The most prominent jet points into the countering pressure of solar radiation and the solar wind. That does not automatically imply motion toward the sun across vast distances, but it does imply that whatever is being seen retains a sunward geometry long enough to dominate the image. This is why the earlier Hubble view from July 21, 2025 is invoked as more than background. The July view is described as already showing a tightly confined sunward feature, one that is on the order of magnitude longer than it is wide. And the January view is presented as a later confirmation that the same basic structure persists and becomes clearer. Two dates separated by months matter because they reduce the chance that a single transient viewing alignment, or a single processing artifact, is doing all the work. The object is not caught in one peculiar moment. It is followed, and the unusual feature remains present. That continuity pushes the discussion away from the easiest explanation for antitales, which is perspective. A projected dust sheet can indeed look like a sunward spike when geometry is favorable, but such a feature is expected to evolve strongly with viewing angle. It can be striking, but it is also fleeting in a predictable way. The sample argues for something more persistent and more structurally rigid, closer to a jet than to a projection. The sample also insists that the anomaly is not confined to the processed image. Even without filters, the coma is described as leaning toward the sun, so the raw brightness distribution already suggests an unusual asymmetry. If that is correct, then the processing step is not creating the sunward structure from noise. It is isolating and clarifying an asymmetry that exists in the basic light pattern. This double appearance, one in raw form and one sharpened by processing, makes the January observation feel less like a trick of technique and more like a constraint on any explanation. The object appears to present significant material or brightness sunward at a time when it is traveling outward. That is the claim that forces the mind back to fundamentals. If the material is typical fine dust, sunlight should push it outward strongly, and the sunward presentation should be short-lived. If the material is ionized gas, the solar wind should pull it outward even more decisively. The sample therefore turns attention to the idea of atypical particle size. If the grains are larger than the usual microscopic dust, radiation pressure is less effective at altering their trajectories quickly. Larger particles can carry their launch direction farther, and they can preserve a narrow stream longer before the environment reshapes them. Yet that idea introduces a second problem. Large grains require more energetic lifting because they are heavier and harder to accelerate. As the object recedes from the sun, the energy available for outgassing generally decreases, making the lifting of large grains more difficult, not less. The January observation is framed as an inversion of that expectation, a later stage where a feature that would seem to require strong, organized ejection remains prominent. That inversion does not rule out a natural origin, but it demands a careful balance of conditions that is not usually required for an ordinary comet: an active mechanism that persists in colder space, a supply of larger grains or aggregates, and a geometry that keeps the sunward structure visible as the object's distance grows. The sample adds a layer of context about how such claims are received, noting that a discussion of this kind of sunward feature can be treated as marginal by some gatekeepers of mainstream publication, not because the data are hidden, but because the subject sits at the edge of what the broader community expects to matter. Without repeating any specific wording, the sample conveys that an early submission on the topic is met with an editorial judgment that the result is of limited general interest. That response becomes part of the narrative tension, because the January image is presented as a clear visual anomaly rather than a subtle statistical effect. If the image truly shows a dominant, tightly confined sunward jet with a structured set of additional jets, then the question of interest seems to come down to whether the anomaly is real and repeatable, not whether it is fashionable. The January 7th observation, in the way the sample frames it, therefore operates like a hinge between simple description and deeper unease. It offers a concrete scene with measurable language, a triple jet pattern, a dominant anti-tail, a narrowness that persists, and a proportion that invites comparison. It also stands at a time when the object is moving away from the sun, when the most conservative prediction is fading and simplification. Instead, the scene is described as sharper and more organized. The data do not yet dictate a single explanation, but they narrow the path forward. Whatever 3i Atlas is doing, the January image suggests it continues to produce directed structure, and it continues to do so in a way that keeps the sunward component central, as though the usual outward forces are not fully writing the story. A jet is not only a stream of material, it is also a pointer. When a narrow feature persists across multiple observations, it begins to imply something about orientation, rotation, and stability at the source. The sample account takes this implication seriously and treats the anti-tail not as a passing visual oddity, but as a signpost that might reveal how 3i Atlas is positioned in space. The reasoning begins with a simple observation. In earlier images, as the object approaches the sun, the sunward jet does not remain perfectly fixed. It shows a small change in its apparent direction over time, described as a wobble around a central axis. If that wobble is real and not an artifact of processing, it carries a specific meaning. A wobble suggests rotation. It suggests that the nucleus, or whatever central body anchors the emission, is spinning, and that the jet is tied to a particular region on that spinning body. When a spinning body emits from a fixed active area, the apparent direction of the jet can sweep out a cone in space. Depending on the viewing geometry, that sweep can look like a back and forth change in angle, or like a spiral pattern in the inner coma. Ordinary comets show this kind of behavior, and it is one of the ways astronomers infer spin states. The sample account then makes a stronger claim. The wobble indicates that the rotation axis itself is oriented close to the direction of the Sun, within about 7 degrees, at least at large distances. The phrase "within 7 degrees" is important because it translates a vague impression into a constrained geometry. It suggests that the body is not oriented randomly. Instead, it suggests that its spin axis is nearly sun-pointing, so that an active area near a pole could produce a jet that remains approximately aligned with the sun direction, even as the object moves along its path. In a natural comet context, that configuration is possible. A jet can remain stable if the active area lies near a rotational pole, and if the spin axis remains stable in inertial space over the observation period. But the sample's concern is not that this configuration exists, it is that it appears to exist together with other alignments that seem to compound the improbability. The sample describes a second geometric feature. The trajectory of 3I Atlas appears closely aligned with the ecliptic plane, the plane defined by Earth's orbit around the Sun and shared approximately by many planets. Many objects in the solar system travel near that plane because they formed from a flattened disk. Interstellar objects, in contrast, are expected to arrive from arbitrary directions, with no preference for the ecliptic. If an incoming interstellar body happens to pass through near the ecliptic, that is not impossible, but it is not required. The sample frames this as an alignment that is already somewhat unlikely by chance, and then argues that, when combined with a spin axis pointed close to the Sun, the combined geometry becomes extremely unlikely. It describes each alignment as having a probability below 1%, and suggests that their combination falls below a level on the order of 1 in 100,000. That numerical claim is presented in the sample as a way of expressing intuition with a quantitative flavor. Two rare alignments occurring together can feel far less likely than either alone. In a careful documentary voice, this point must remain clearly labeled as an inference rather than a measurement carved into stone. Probabilities of this kind depend on assumptions. They depend on how tightly the alignments are defined, on how random is modeled, on how selection effects work, and on how much the observer's attention is drawn to unusual cases after the fact. A rare-looking alignment can be less rare if the criteria are chosen after viewing the data, and it can be less informative if a large population is being scanned where one outlier is expected by chance. Still, the sample's argument has a defensible core even with those cautions. If the observations truly suggest both a near-ecliptic trajectory and a near-sun-pointing spin axis, then the object's geometry is not merely odd in one way. It is odd in a coordinated way, with multiple lines of orientation converging on the Sun and the planetary plane. That convergence is what deepens the mystery, because it invites an explanation that links the alignments rather than treating them as unrelated accidents. The wobble claim also resurfaces in the outward phase, after perihelion, when the object is moving away from the Sun. The sample suggests that a similar wobble persists as 3I Atlas recedes, implying that the orientation remains similar rather than flipping or becoming chaotic. Again, this can happen naturally. A comet nucleus can spin in a stable manner for months. Yet the sample emphasizes that the persistence of the antitail while receding is already the central contradiction, and a stable sunward-pointing axis would, in principle, help maintain that contradiction. It would provide a mechanism for why the sunward feature remains sunward rather than sweeping into a broad fan. The antitail, in this view, is not merely a tail. It is the visible expression of a stable geometry. That framing creates a tension with the simplest comet expectations. A typical comet's most dramatic changes are driven by distance to the Sun. If the object continues to show strong, organized emission while far from the Sun, then either it remains more active than expected for its distance, or it is releasing material in a way that remains visually organized despite weaker energy input. If the axis is sun-pointing, then the Sun is not merely the energy source. It becomes the reference direction around which the object appears to arrange itself. That is the part that feels unsettling in the sample account. Not because it cannot happen, but because it seems to happen at the same time as other low-probability alignments. Conservative explanations remain available, and the narrative does not need to discard them. A sun-pointing axis could arise by chance. It could also arise through torques, gentle twisting forces caused by asymmetric outgassing. When gas leads a rotating body unevenly, it can act like a small thruster, gradually changing spin rate and spin axis orientation. Over time, outgassing torques can reorient a nucleus. Whether such a process would naturally drive an axis to align with the sun is not guaranteed, but it is a plausible pathway for changing orientation without invoking exotic causes. Another possibility is that the anti-tail is not a jet fixed to a vent at all, but a dust structure dominated by geometry, and that the apparent wobble arises from changing viewing angles and evolving dust distribution rather than from nucleus rotation. That possibility remains consistent with known anti-tail behavior in some comets, though it would need to reconcile the reported tight collimation and dominance of the feature. The sample's emphasis on a stable, narrow structure is what pushes it toward a jet interpretation rather than a purely geometric one. The importance of this section is not to claim a final answer, but to show how a single, persistent feature can transform from a curiosity into a constraint. If the anti-tail behaves like a jet tied to rotation, then it encodes information about spin state. If it remains oriented toward the sun, it implies a sunward relationship in the object's geometry. If that sunward relationship appears alongside a near-ecliptic trajectory, the object begins to look less like a random passerby and more like a body arranged in a particular way relative to the solar system's main plane and the sun itself. None of this proves design, and the documentary tone must avoid pretending it does, but it does narrow the field of comfortable explanations. A natural comet can be peculiar in one respect and still be ordinary in the rest. 3I Atlas in the sample account presses for attention because multiple aspects of its geometry appear to lean in the same direction, toward alignments that are not required and not easily dismissed as noise. The wobble and the axis claim therefore deepen the narrative's central question. The object is not only active when it should be fading. It is also, at least as interpreted through these images, oriented in a way that keeps the sun at the center of its visible behavior, as though the sun is not merely shining on it, but somehow defining how it presents itself as it departs. The particles themselves become the next puzzle, because they link what is seen to what can physically persist in that shape. The sample account proposes that the sunward jet and its stubborn narrowness could be explained if the material involved consists of grains larger than typical comet dust. Normal comet dust is made of microscopic particles, easily influenced by sunlight and by the flow of charged particles from the sun. These fine grains scatter light efficiently, creating the broad, soft tails that are familiar in most comet imagery. They also disperse quickly because each grain feels a measurable push from radiation pressure, the small but continuous outward force of sunlight. Larger grains behave differently. A grain several times, or hundreds of times larger than the average dust particle, has more inertia and a smaller surface area relative to its mass, so the push from sunlight changes its motion less rapidly. The larger the grain, the longer it can keep its launch direction before the solar environment reshapes its path. In that sense, larger particles can preserve a jet's original direction and keep it narrow for longer. The difficulty is that lifting such grains is harder. Outgassing from sublimating ice must act as a jet of gas that pushes them away from the surface, and the weaker that gas flow, the harder it is to launch heavy particles. As 3I Atlas travels farther from the sun, sunlight becomes weaker, surface ice warms less, and gas production should decline. In that setting, a sunward jet made of large particles ought to fade more quickly than a jet of fine dust close to the sun, not the other way around. The sample account holds to this contradiction. The simplest physical expectation fails because the strongest visible structure remains the one that should weaken first. The persistence of this feature therefore forces attention onto the properties of the material itself. If it is not ordinary dust, what could it be? The narrative keeps within plausible boundaries, suggesting that the material must occupy a middle regime. It must be large enough to resist the push of light and solar wind, but small enough to be gradually eroded or destroyed once it reaches hundreds of thousands of kilometers from the nucleus. That phrasing creates a narrow window of possibility. Particles in this regime could maintain a sunward orientation briefly before being ablated by the environment, producing a visible anti-tail that eventually dissolves into diffuse light. Yet for this to happen, the comet would have to supply such particles steadily even while the sun's heat diminishes. One possible natural explanation involves composition. Some ices sublimate at very low temperatures, releasing gas even far from the sun. If those ices are buried under layers that become more porous as surface material fractures, they could continue to vent. Carbon monoxide and carbon dioxide are common examples of such ices. They can sublimate where water ice would remain solid. If 3I Atlas has pockets rich in those volatiles, it could remain active longer than a purely water-driven comet. But the observed directionality complicates that picture. Randomly distributed pockets should produce diffuse emissions, not a single dominant sunward jet. A second possibility is that the jet's structure is shaped not by gas pressure alone, but by cohesion among the particles. Clumping or binding effects could cause grains to leave the surface together, preserving alignment for longer distances. Such behavior might arise if the particles are coated with organics, or if electrostatic forces help them stick temporarily. These effects are speculative, but not unphysical. They introduce mechanisms that could maintain narrowness without requiring extraordinary external forces. Still, the sample narrative emphasizes that whatever these grains are, they are unusual when compared with the microscopic dust typical of comet tails. Their size must be sufficient for them to resist immediate acceleration by solar radiation pressure, and their composition must allow them to persist long enough to travel significant distances. The fact that these particles would eventually be destroyed by the solar wind also helps explain why the antitail remains finite rather than extending indefinitely. It has an observable length, suggesting that the material survives only to a certain range before being dispersed or vaporized. The proposed interplay between particle size, density, and lifetime creates a coherent physical framework, yet it does not remove the discomfort. The antitail remains aligned against the dominant forces for a surprisingly long time, and its persistence while the object recedes is the point where this framework stretches thin. The sample also notes that even with the introduction of large particles, the directional consistency and the appearance of secondary jets perpendicular to the solar wind remain hard to duplicate with a purely mechanical model. These perpendicular features, if they exist as described, imply that the ejection pattern is not governed entirely by random surface vents or by sunlight-driven sublimation alone. Something appears to organize the release into stable directions that maintain separation in angle. In most natural examples, multiple jets arise from complex rotation and uneven heating, but they tend to blend or twist into broad fans rather than stand as distinct linear features that preserve their angles with respect to the sun. At this stage, the story edges into the threshold between data and interpretation. The presence of large grains explains persistence, but not geometry. Orientation explains geometry, but not persistence. Together, they form a tension that the sample treats as central to the mystery. The physical picture must accommodate jets that act as if they are both highly stable and continuously fed, yet not dominated by the sun's outward pressure. The broader implication is that the visible behavior of 3I Atlas is not easily decomposed into a single variable, such as distance, rotation, or composition. It appears to demand a coordinated set of conditions that hold steady as the comet moves through changing energy environments. The simplest expectation for any natural comet is gradual simplification as it cools. Instead, 3I Atlas presents increasing complexity, a visible system of directed structures that seem to resist both dilution and randomization. The question of what these particles are thus merges into a deeper one. What kind of object continues to release organized material as its environment becomes less conducive to activity? A curious feature of the 3I Atlas story is that two narratives can run in parallel without ever fully meeting. One lives in processed Hubble imagery and in careful discussion of jets, dust behavior, and geometry. The other lives in simplified public diagrams that present the object as an ordinary comet, moving outward with a tail that trails away from the sun. The tension matters because the anomaly described in the sample is concrete and visual. It is a claim about direction, a sunward-facing structure that remains prominent even as the object recedes and should be calming down. The sample points to a public Skytrack graphic attributed to the British Broadcasting Corporation, showing 3I Atlas after perihelion as if it is traveling tail first, with the tail pointing away from the sun in the conventional way. This is a reasonable default for a general audience. Most comets do show their most extended visible structures pointing away from the sun, shaped by radiation pressure and the solar wind. A simple graphic is built to communicate motion and location, not the complicated inner structure of the coma. It is tempting to interpret that mismatch as concealment, but the more ordinary explanation is momentum. Once an object is classified as a comet, a large number of downstream products reuse that classification. Outreach visuals, sky maps, automated summaries, and familiar language about tails and fading. Revising those products is possible, but revision usually follows consensus, and consensus in science is deliberately slow. A sunward feature can be placed into an existing category, such as a projection-driven anti-tail, and once it is placed there, the urgency to update public material often fades. A second layer is the way visual evidence is curated. Filtered comet images can look strange, even when the filters are standard tools in research. Rotational subtraction suppresses the circular coma and makes jets stand out, but it can also make an image look less like a photograph and more like an abstract pattern. Editors who want immediate clarity may prefer an unprocessed view, even if that view hides the structure that matters. This preference does not require bad faith. It is a choice shaped by how quickly an audience can recognize what it is seeing. There are also legitimate scientific cautions that reinforce this conservatism. Comet tails are three-dimensional structures projected onto two dimensions. A feature that looks sunward can be dust arranged along the orbital plane and viewed close to edge-on. A coma that looks brighter on the sun-facing side can result from uneven activity or from a recent outburst, with sunlight illuminating fresh material. A narrow streak can also be created or exaggerated by imperfect alignment, motion blur, or residual background structure after subtraction. Because these pitfalls are real, the bar for declaring that an object is doing something physically unprecedented is high for good reason. What makes the communication gap significant is the trend described in the sample. The claim is not merely that an anti-tail appears, but that it becomes more prominent as the object travels away from the sun. If the anti-tail is only a viewing effect, it should evolve strongly with geometry and often weaken when the viewing angle changes. If it is a jet of material launched with enough momentum to remain sunward for a while, it should weaken as solar heating drops and outgassing declines. A feature that stays strong, stays narrow, and stays central in the outward phase pushes against both expectations and makes the default narrative feel less secure. The sample frames the reluctance to pivot as a matter of credibility rather than conspiracy. Researchers and institutions build trust by avoiding dramatic claims until repeated evidence forces a change. If an early description turns out to be incomplete, revising it can be uncomfortable, and discomfort alone can slow revisions, even in good faith. This human factor sits alongside technical caution. It is not a plot. It is the slow friction of changing a public story while the data are still being argued over. The gap can widen further when different teams focus on different data products. One analysis might treat broadband images as primary and judge the object by overall brightness and by whether a conventional tail is obvious. Another analysis might treat inner coma structure as primary and apply a rotational subtraction filter to the same exposures, placing emphasis on a narrow sunward jet and on secondary jets that appear misaligned with a simple outward flow. Both approaches can be responsible, yet they will speak different languages, and each will choose figures that support the language they are using. In a calm documentary reading, this reluctance becomes another observable pattern rather than an accusation. The object produces images that some analysts interpret as a dominant sunward jet and a strangely oriented coma. Standard comet processing methods are used to reveal that structure, and comparisons to ordinary comets are used to argue that the result is not simply a trick of technique. Meanwhile, public graphics continue to show the object behaving like a normal comet. The questions therefore narrow rather than explode. Are the same features recovered by independent teams processing the same data? Do the features persist across multiple dates and multiple instruments? Does the raw imagery, without specialized filtering, show a consistent sunward bias in the inner coma, as the sample claims? The mystery here is therefore not only in the sky. It is also in how quickly a community can update its working picture when an object behaves in ways that are awkward but not yet decisive. 3i Atlas continues outward, and the simplest story wants it to fade into routine. The sample insists that routine is not what the images show, and that the public story lags behind the most troublesome details. If the anomaly fades, the lag will be forgotten. If the anomaly persists and strengthens, the lag becomes part of the record, a sign that the simplest model will stop matching what the sky continues to show. The question of how unusual 3i Atlas is cannot be separated from a wider question about how often anything like it should appear at all. Interstellar objects are no longer hypothetical visitors. In recent years, at least a small number of bodies are identified on trajectories that suggest they arrive from beyond the solar system, rather than from the long, familiar reservoirs of comets and asteroids bound to the sun. The basic expectation that follows is simple. If one or two are detected with limited surveys, then improved surveys should find more. More sensitive instruments, wider fields of view, and faster data pipelines should increase the detection rate, not decrease it. This expectation becomes part of the background pressure behind every new claim about 3I Atlas. If interstellar visitors are common, then one peculiar object might be less shocking. One outlier among many, perhaps a rare but natural kind of comet from a different star system. If interstellar visitors are rare, then a single object that appears to combine multiple anomalies gains weight, because there may not be many chances to test competing explanations against new examples. The sample account places particular attention on the Vera Rubin Observatory, a facility designed to survey the sky repeatedly, building deep, time-based maps that reveal faint, moving objects. Its wide field and repeated scanning are well suited to catching fast-moving visitors, including those that arrive on unexpected paths and fade quickly. The sample presents a striking claim that after the observatory is fully active for roughly half a year, it has not yet revealed the expected stream of new interstellar bodies. This claim needs to be handled carefully in the narrative because the exact pace of discovery depends on observing cadence, commissioning stages, pipeline maturity, and the simple fact that nature sets its own schedule. A lack of detections over a limited time could be meaningful, or it could reflect ordinary delays and thresholds. Still, the sample's point is not a formal statistic. It is a mood of tension between promise and reality. If a powerful survey spends months watching the sky and does not immediately uncover a crowd of interstellar objects, then the sky begins to feel quieter than some predictions suggest. In that quieter sky, 3I Atlas stands out more sharply because the mind cannot easily file it into a rapidly growing catalog of similar visitors. The rarity question also interacts with selection effects, the hidden biases that decide what is found and what is missed. Interstellar objects may be common and still hard to detect if most are small, dark, and fast. A fast visitor can cross the inner solar system quickly, and by the time it is bright enough to be noticed, it may already be receding. Many surveys are optimized for known populations and may discard unusual motion patterns as artifacts until the pipelines are tuned to recognize them. Even with a dedicated survey, software choices and human review influence what becomes a confirmed discovery. These practical constraints mean that a short period without detections cannot prove rarity, but it can still shape how a single object is interpreted. If the sky does not supply a steady stream of interstellar comparators, then the burden of explanation concentrates on the few that are already under observation. 3I Atlas, in the sample's framing, is not only interstellar, it is also unusually interactive with the inner solar system in a geometric sense. It passes several planets, and the sample highlights close approaches to Venus and Mars, with Jupiter mentioned as a significant encounter within months. Close approaches do not require intention. They follow from the object's trajectory and the planet's positions at the time. Yet, a path that threads past multiple planets can still feel consequential because it multiplies opportunities for observation and multiplies opportunities for speculation. Every approach creates a chance for new images, new measurements, and new interpretations. If an object is already suspected of unusual activity, then each encounter becomes a new test of whether the anomaly persists, shifts, or fades. In a conventional comet picture, the dominant evolution is driven by distance from the Sun. Planetary flybys matter mainly for observation geometry, not for changing the object. In a more speculative reading, the flybys can be imagined as waypoints, moments when the object's behavior could change in response to environment, illumination, or unknown internal triggers. The documentary voice does not need to claim that such changes occur. It only needs to note that the timeline creates natural checkpoints where observers watch closely for any shift. The sample's emphasis on continued observation reflects this. If the antitail strengthens as the object recedes, then it becomes more than a perihelion effect. If the triple jet pattern remains stable across months, then it becomes more than a brief outburst. The broader interstellar context sharpens the question of what kind of object could behave this way. A natural comet from another star system could carry a different mixture of ices and dust than typical solar system comets. It might contain more volatile compounds that remain active at larger distances. It might have a different internal structure that vents in a more collimated manner. It might even be an object that has been processed by radiation and cosmic rays for a long time, building a crust that fractures in unusual patterns when warmed. These ideas remain within ordinary physics. They do not require technology, only diversity. Yet the sample's narrative keeps returning to the same sticking points: the prominence of the sunward feature relative to conventional tails, the tight collimation of the antitail, the apparent orientation of the rotation axis near the sun direction, and the combination of these alignments with a path near the ecliptic. If interstellar objects are common, then one might expect to see a range of strange behaviors, some of which could resemble this. If interstellar objects are rare, then the temptation grows to treat 3I Atlas as a singular event that deserves wider attention than it receives. This is where the documentary tone can remain calm while still building unease. The absence of many comparators does not prove that the object is artificial, and the narrative must not pretend otherwise. It does, however, limit how quickly an anomalous behavior can be normalized. Without a larger sample, the question remains open longer. The uncertainty persists, and the object's continued visibility becomes a kind of pressure on interpretation. Each new image either relaxes that pressure by revealing a more ordinary pattern, or increases it by reinforcing the same contradictions. The sample leans toward the second outcome. It presents a world where the expected flood of new interstellar discoveries has not yet arrived, while the one major interstellar visitor in view continues to deliver features that appear inconsistent with a simple fading comet. In that world, 3I Atlas becomes not merely a curiosity, but a probe of the limits of current categories. It forces a choice between expanding the natural range of comet behavior and entertaining the possibility that the category itself might be wrong. The story does not require that choice to be made yet. It only requires that the choice remains difficult to avoid. The object keeps moving outward, and the solar system does not provide an immediate replacement for comparison. If new visitors soon appear and behave plainly, then 3I Atlas may become the exception that proves the rule, an outlier with a natural explanation that is simply unfamiliar. If new visitors appear and share even a fraction of its strange traits, then the exception becomes a pattern, and the pattern demands a new framework. Until that evidence arrives, the unease remains grounded in a practical fact. There may be very few opportunities to watch an interstellar body closely, and one of those opportunities is unfolding in images that seem to resist the most comfortable story. By the time 3I Atlas is moving outward through the colder reaches, the story becomes less about a single strange image and more about what remains strange after ordinary corrections have been applied. A natural comet can look surprising in one snapshot and then settle into a familiar pattern as geometry changes, as outbursts subside, and as the sun's influence wanes. The sample account argues that this settling does not happen here. The most prominent feature stays stubbornly sunward. The antitail remains tightly confined in the processed views, and the raw coma brightness is described as leaning toward the sun, when it should be drifting into a simpler, more symmetric glow. The January 7, 2026 Hubble observation is treated as a firm anchor, not because it answers the mystery, but because it sharpens what needs to be answered. A triple jet structure is described, with a dominant sunward jet that appears long relative to its width, and with two weaker jets arranged in a way that seems orderly rather than accidental. Even a cautious reading must acknowledge that a geometry like this, if it is repeatable and not a processing artifact, narrows the range of easy explanations. The most conservative pathway is still to expand the natural category rather than abandon it. A comet from another star system may bring unfamiliar mixtures of ices, dust, and internal structure. Low-temperature volatiles can sustain activity farther from the sun than water ice alone. A fractured crust can channel gas through narrow vents, producing collimated jets. A spin axis that happens to point close to the sun direction can maintain a persistent sunward jet if the active region lies near a rotational pole. These elements are not exotic on their own. The tension comes from how many of them must align at once to fit the reported behavior. The sunward feature must be prominent relative to conventional tails. The particles must resist solar radiation pressure long enough to preserve a sunward extension, yet also be limited in range, disappearing at hundreds of thousands of kilometers rather than extending without end. The activity must persist while the object recedes. The geometry must remain stable over months if the wobble and axis inference is accurate. Each condition can be granted individually. Together, they begin to look like a special case that demands either a rare natural combination or a missing piece in the interpretation. The sample account dwells on that missing piece by returning to what a tail is supposed to record. A tail is the visible signature of how material responds to sunlight and to the solar wind. If the record appears inverted, one possibility is that the observer's reading of the record is incomplete. A projection-driven anti-tail can look sunward without requiring sunward motion. A dust sheet along the orbital plane can compress into a line when viewed edge-on. A bright asymmetry in the coma can reflect uneven activity that happens to be stronger on the sunward side. These mechanisms are known, and they provide a legitimate caution against turning an odd image into an extraordinary claim. Yet the sample insists that the anti-tail of 3i Atlas is not merely a projected dust trail, because it is described as unusually narrow, unusually dominant, and persistently emphasized across multiple dates and processing comparisons. If that insistence is correct, then the anti-tail is not only a matter of viewing geometry. It is a persistent structure that behaves like a jet with its own stability. At this point, the narrative opens a controlled space for speculation, while keeping its footing on the observations. If 3i Atlas is a natural body, then the most unsettling feature, the sunward jet, must be an outcome of material properties and orientation that are uncommon but still possible. If it is not a natural body, then the same features can be read differently, as though the object is not simply venting, but directing, maintaining collimation and alignment for reasons that are not easily derived from sunlight alone. The sample account gestures toward this second reading without treating it as proven. It notes that a lack of obvious radio emissions does not settle the question, because there is no reason to assume that any technological activity would announce itself through narrowband radio signals in a way that current searches would reliably detect. It also notes that the absence of a conventional technosignature does not eliminate the possibility of a modified object, an engineered structure, or a carrier of smaller devices that could operate quietly. Such possibilities remain speculative by necessity, and the narrative keeps them tethered to the single feature that motivates them, the persistence and geometry of the sunward jet. If the jet truly defies the most familiar expectations, then it becomes tempting to ask whether the object is doing more than passively reacting to the sun. The sample account extends this temptation into the planetary encounters. A body that passes near Venus, Mars, and later Jupiter invites attention simply because it provides checkpoints for observation. It is possible to imagine that such checkpoints could matter to an artificial visitor, but it is equally possible that they are accidental alignments along an interstellar trajectory. The documentary voice remains careful here, because the same fact can support multiple stories. A close approach to Mars, for example, can be described as a major scientific opportunity without implying intent. The sample account introduces a further claim that a team has examined imagery from the Perseverance and Curiosity rovers after the Mars encounter and has noticed something that is not yet sufficient for a full analysis. This claim must remain framed as a report rather than as a settled finding, because no specific evidence is provided in the sample beyond the assertion. Still, even as a reported effort, it illustrates the psychological effect of persistent anomalies. When a sky object seems to resist ordinary explanation, attention spreads to related data streams, and the search for corroborating oddities expands from telescope images to rover panoramas and mission archives. The sample account insists this expansion is not driven by a desire for conspiracy, but by the stubbornness of the primary anomaly. The narrative also addresses the social dynamics without dramatizing them. It suggests that many astronomers have strong incentives to interpret 3i Atlas as a comet, partly because that is the most probable category, and partly because scientific credibility is built on resisting sensational conclusions. In this view, reluctance does not imply suppression. It implies caution, and the cost of changing a public claim once it has been made. That cost can slow acknowledgement of an anomaly, even when the anomaly is visually striking. The result is a prolonged period where images and interpretations circulate in parallel, with specialists debating whether the sunward feature is an anti-tail driven by geometry, a jet of unusually large particles, or a sign of a deeper mismatch between the object and the usual comet model. The story therefore ends where it begins, with the same simple expectation and the same persistent contradiction. Distance from the sun should lead to fading activity, weaker jets, and a more conventional tail structure. 3. I-Atlas, as described in the sample account, continues to show a sunward-oriented feature that becomes more obvious rather than less, a narrowness that resists dispersion, and a geometry that seems to hold steady when it should be relaxing into routine. The open questions remain practical and specific. Do independent analyses reproduce the same dominant sunward jet across the same dates? Does the feature persist as the object continues outward and approaches new checkpoints in its path? Can the particle size and composition needed to support a long, narrow sunward structure be reconciled with the declining energy available far from the sun? If the alignments inferred from wobble and axis orientation are real, do they point to rare natural coincidence, or to an as-yet unrecognized physical mechanism that can drive such alignment? 3. iAtlas keeps moving, and the solar system offers only a limited window to watch. The anomaly, whether natural or not, remains unresolved, and the sky does not yet provide enough comparators to make the category feel secure. In that uncertainty, the object's most unsettling trait is not what it might be, but how long it continues to behave as though the familiar rules are still being tested.